We're continuing off from this little hop. I realized what I did. It's just a typo. Um, Technically, you need the mean value theorem, whatever, but technically, you can also just look at it and just say, yeah, that kind of makes sense. And then just said, yeah, because it's minus d, it's like minus d is like a delta. And it works out in the end, but the real proof goes from, starts from integrals and goes to mean value theorem and does that, but eh, you can, it's not recursive, actually, it's not recursive actually, so it's fine. Um, Either way, you can figure it out. Anyways, we're in the intro to integral. So first thing we do is Riemann sum. And here the Riemann sum, I do want to mention this version over here. So why did I give this version? It's because this version gives off the idea of what was it called? The idea of Cartesian. This is the Cartesian version of a Riemann sum that works out, basically, is what I'm trying to put down. Yeah, I'm trying to put down that, yes. Um, yeah, I'm trying to put down that because we're gonna go with the more loosey-goosey version. There's actually a more formal version, a very more formal version that I don't think we need, but I did put down. It's gonna take me forever to find it, isn't it? Let me just start. Yeah. All right. No, that's better, right? So let me get to over there. Basically, let me Okay, I don't see it, so I give up already. I don't think I actually put it down here. I think I actually put it down on the definitions, and you need to go all the way down over here. Yes, this is what, but this is the most beautiful definition that you can ever think of, and the most fundamental. And you need to use a lot of pain to actually figure that one out. Um, but yeah, so I'm not using that, frankly. No. We're using a simplified Cartesian version of it. And then we're going to modify this to a non-Cartesian format a little bit. But just a tiny, tiny expansion on the original idea. Not the big ass expansion that goes for cover everything, but it covers a lot. So it covers enough. By cover a lot, it covers a lot of methods. But because when you're desperate and you don't know what the shit you're doing, you always go down to the most fundamental versions of it always. And here's one of the fundamental version of it. Basically, you have to do indexing over here. This is considered indexing over here. This version over here. Now, this delta x is special. It's not really a delta x. It says x divided by n, but x implies is a function of this basically, and then you're just scoofing it down. It's a very nuanced but interesting way that makes it interesting. Why? Because you can see that this delta x is actually equal to this, which you can get to this format over here. Um, yeah. It works. It works. And then you take a little bit of this, and then x goes out, x squared goes out, basically getting this version over here, which is definitely the, if you take a derivative of that, you get this basically. Um, yeah. So quickly, you need to go to section 3.2 for this one because that's why I made that factorial shenanigans in trig because we absolutely needed that over here in 3.2. If you go back there, it was factorials and summations, and it was absolutely necessary there. That's why I did cover that. Anyways, what was I again? So summation of n to I equal to 0, and then you take a limit of this to x to infinity, basically. And this is by and then you do fxi index to delta x. And this is delta x. So delta x has to be very, very small. And we're going to make it basically 0. And how do we do that? Well, x as a function, no matter what, it's going to go up over here. And then we take a n over here, which makes it go to infinitely down, negative infinity. So you're condensing it a little bit. but you're not really condensing it a normal way because its x is a function that in the going all the way. So you're indexing and then you're just indexing as you go to x like that. It's a very weird way, and I don't think this clearly visualizes it enough. But and that's what happens over here. And then as you add those up, basically you can figure out that this I and this summation needs to be transformed into this format so this n can actually cooperate and actually work out here. Now, we did a lot of limits on this before, so I'm not gonna mention how to do this because it's kind of clear. And we do the same thing over here. Again, that's why section 3.2 was so important. Um, and then section 3.2 is important again because it allows us to solve this one too, basically with a geometric series. And then again, if you look at 3.2, there's geometric series down over there. There's no questions for it basically. It's down bare dry. I need to make more questions about it. But it shows you what it's just for Riemann sum basically for now. Later on, it can be also for Taylor series and ratio test, but for now, it's for Riemann sum. Yeah. So with a lot of algebra, you can figure out this format over here, which goes to EX. And over here is a really interesting thing. This is a constant, so we can move to C. C is a constant too, and the C is a general constant, so this a constant doesn't matter. Anyways, yeah, I can't explain this, but at the end of the day, do I need to explain it? I kind of need to. No, I just want to explain the easier way to you. So you know how a derivative of this is basically EX. Don't do all this. Just realize that there's a derivative of it and just take the integral and just realize it. It's much easier. The reason I'm doing all this is just to prove that it works. I don't really want anyone to do it that way. It's painful and it took me forever to do this. And this is the only one I'll explain. I mean, I explained one of them thoroughly. I'm gonna explain this one thoroughly because this is not taking the regular, we're expanding the definition of the Riemann sum to a more to more accurate the more but what that means is that there's a problem. As you can see over here, if we do the original way, there's a problem. And now we have to go and expand the definition to the more formal definition, the more hardcore basic version of it. Is basically what's happening here. And over here, you realize that this is indexing that we talked about. So basically what's happening is now we have an I and I minus one. Minus one, I guess, is this one. So this is a minus one I. So why is that important? Well, we did that. We showed that over here, but it really did nothing because it didn't matter back then because x minus n, we just drew it to zero basically, and it's just like x squared anyway. So it worked out over here, but it didn't work out over here because if you use that same method, original method is saying basically this is the integral. Now you get the index over here. You start off with infinity. You start off infinity. And there's a problem here. That's what's happening. You're indexing to infinity, and it doesn't work out really well. So over here, we introduce this thing that really just shifts our entire frame with and in is just infinity zero. So we do zero is just one over here. So you just I really don't know how to visualize it, but it's not doing the regular this thing. It's like Jacobian matrix kind of thing. Um, but yeah, and then after that, you're just following through with some algebra. Yeah, I need to figure out how to visualize Jacobian matrix because Jacobian matrix, I was trying to make a model of it, but it didn't really work out. I know what it is. It's just a fit, but it's just not working out in my animation. And when I tried to visualize it by drawing it and everything. It just doesn't look good. So, anyways, the next one is definite integral, which seems easier because was at first, but then you realize it's a little bit has a has more subtlety to it. The first thing we were going to explain is that yes, you can use Riemann sum again, and Riemann sum is going to be our primary definitioner, which but we're not going to do it. We're just going to go take a shortcut here and just say, well, we already have an antiderivative and we can actually just figure it out. But why can we do that? But we don't want to do this again. We don't want to go through pain. And I know how to do it. We did it in another video before, but we don't want to do this again. So instead, we derive the first fundamental theorem of calculus. And here's where everything just aligns, um, at least to me. So first of all, we split this into two parts over here, and as you can see, I'm going delirious because it's 3:30 now, which means it's already 3 hours and 30 minutes after my bedtime. So great. Over here you see this over here, which this can turn into a more separate part, which finally gets this part. Why is that important? Well, next thing you know, you get this format, and which this format over here with this do, you just divide it by h. Why is that important? So divide by h is nothing. Uh, Once you realize you can take a limit of these, limit of these, limit of this, and limit of this, we realize that this is a derivative. And now, if this same operator causes derivative, we know for a fact that this is equal to this, basically. So let's prove that. And the only way to prove that is by squeeze theorem. Squeeze out the juices to see if it's a limit. And we clearly see that if f minus c, wait a second, this is this over here. I must be dreaming. This over here is basically the formal definition of a limit. Uh, it is clearly the formal definition of a limit. You're squeezing it, and you have a formal definition of a limit here. Oh God, that's the derivative. That's the derivative, and then we just see that that's basically what happened. So that's why this is true. But that's not enough because we have to get rid of the plus c for the finite. So how do we get to that's the fundamental theorem of calculus number 2, where we see that if this is true, you just plug it back in and we just see b, we plug b, okay, we plug a, we realize that c cancels out basically. That's the fundamental calculus part 2. Oh God, now we see the whole point of this. We could just say that this, we take an antiderivative of this, which is xn plus 1 by n plus 1, and then we just plug in b minus a. B over here, and then minus a, it's the same thing. So yeah, that's the power of this. And then we have some do other proofs here, which k can get out of an integral because it doesn't affect the whole thing, and so on and so on. Over here is an interesting one where we say that the integral is a negative version if you flip it. Kind of obvious proof because if you make a negative version of this thing flips basically. Um, if you flip this and take a negative out, this was happening basically. Um, and then you realize that yeah, that was a kind of obvious thing that would happen. So we have fun with this questions like this. It's like a puzzle question, trying to figure out how to flip it properly to get it right. It's a I think it's a common question. Over here you see that the if you put A and A, you just get 0, but that kind of is obvious if you think about it for 3 seconds. If you do the B minus A test, and it's like, hey, that's just obvious. Obviously because the integral is area, because Riemann sum is just adding a bunch of boxes, we see that the average is going to be the divided by the length, which is shown over here. Now, another thing I need to talk about is the mean value theorem for integrals. Oh, I made a mistake here. It's not a mistake until I realize that my I want to be cleaner. That's why I decided to delete those. Anyways, basically it's another squeeze. It's a squeeze of min and max. Oh, that's the integral. We get b minus a. Oh, we already know that from the first and second theorem of calculus, fundamental theorem of calculus. And then why I forgot to delete this. Why did I forget to delete this? Basically saying min and max is like this, and you see that that's the average. When you realize that's the average, you realize that let me get my pen open. Okay, okay. Over here, you see this is the average, and this average is like okay, so that's on the right side is b minus a, on the left side is b minus a. If we, I'm doing that's the thing I messed up here. I messed up hard here. What the hell did I do? Oh, I think I just have to get rid of this because this is FC. The average is FC. Oh, I see. What the hell did I do wrong? No, no, you're right. Yeah, I'm right. I'm right. So I messed up. Over here, if you multiply b minus a, if you get rid of the average part, so it means that you get this part back, which means that you get this. You check mark it, and then you realize afterwards that you could go further with it. Because if you realize this, we know that if you evaluate this, you get this form for the first fundamental theorem of calculus, the second fundamental theorem, uh, part two, basically. And then you get this just division, and you get this thing. So over here, there's some questions, and oh yeah, the last one, this one's a pain in the ass. But I haven't done any questions on it because it's kind of obvious. Clearly, that if you think about it, the absolute value of it is less than just doing the absolute value of the internal because this is internal. If you think about it for 3 seconds without, you don't even need to look at this proof that I made, even though it looks good. Think about this. I think about the absolute value internally. It would be like that, right? But if you took a absolute value after you took an integral of it, it would be zero because this cancels out ahead of time and it makes a line over here. And you take an integral of that, that's zero. Basically, you could think of a sine or cosine or whatever. And basically, you could think of, oh, that's kind of no duh, no duh. I'm tired, as you could tell. I would not say that when I'm not tired, but right now I'm tired. So because it's like 3 hours and 30 minutes past my bedtime, I've been addicted to this making this textbook, as you can tell. I'm